Hey all, this is Mr. Bonifaci. I'm going to go ahead and go over with you guys how Charles' law works, which is our second one. We started with Boyle's law, and now we're kind of rolling to Charles. So if you remember, Boyle's law had to do with the pressure and the volume, and how if you change the volume, you change the pressure, or if you change the pressure, you could change the volume, and how they affect each other. Okay, so anyway, this one is volume and temperature. Okay, so Charles, different scientist, experimented by changing the temperature of a gas and then measuring the volume. Okay, now if we do this in classroom, you'll kind of see what I would have showed you normally, but since I'm not there today, or maybe you're going back over these later, there'll be pictures that kind of show you the same kind of thing. Okay, so you'll notice the same pattern kind of here. Like if I make things hotter, okay, things get bigger. Okay, and there's a constant in here that's going to kind of show up. Okay, now remember on the quiz, which I'm thinking is probably Wednesday next week in our class. Obviously, watch this future years; it won't be that day, but it will talk about two different ratios you need to kind of discuss. Okay, and I guess not two different ratios, two different things. Okay, thing number one is you need to talk about how like you need to be able to talk about how it actually functions. So you'd explain something like, if things get hotter, the particles move faster. Remember, we talked about the kinetic theory of matter. Okay, so hot particles move faster. More speed means they take up more space. Okay, because they're going to be pushing outward more, so they'll be bing 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 bing, bing faster. Okay, and because of doing that, they're going to take up more space. So again, hotter things move faster because of kinetic theory of matter, and therefore they take up more space. Okay, so in that same way. Okay, so cooler gas, less volume; hotter gas, more volume. And here's why. You need to explain that. And the second thing, and here's a good example. This is what we would have done in room, right? So you can blow up a balloon, and I put it in ice and I measure it, it's going to be smaller. Okay, and I take that same balloon, not let anything out, and I put it in really hot water, whether boiling or not, it's going to expand. The particles are bouncing around larger and they're pushing outward more. Okay, because they're moving faster. The balloon will take up more space, be larger. Okay, so now, we talked a little bit about this before, and this is one of the things that Charles noticed, that he couldn't measure down to absolute zero. Okay, but he figured out, like, if you take a bunch of data on this first gas sample, and a bunch of gas on this gas sample, and a bunch of data on this gas sample, all the lines that you graph seem to go backwards to the same point, which in Celsius, and you'll notice here it goes farther than we go, but negative 273 degrees Celsius. And he goes an extra couple points there, 0.15, and there's probably other points past that. But the big thing here is negative 273 Celsius is absolute zero. That is the temperature. Remember, we were talking about everything's moving, but that is the temperature where everything stops moving. Now, theoretically, because remember, we can't get that cold, you can get, like, we can't even get anywhere close, but hypothetically, you can get infinitely close to it, and but not actually get there. It's kind of like the speed of light. Like, it would break things. Like, without matter moving, it wouldn't take up space, which would affect time. Blah blah blah. Things break on a physics level if you get down to absolute zero. Okay, so in Kelvin, 0K is absolute zero. So for this law to work, okay, you need to convert Celsius into Kelvin. And here is this, and this is what I want you to write down. First thing, well, let me go back. Okay, so I should have been talking a little bit more about what you should have written down. So depending on how you feel about stuff, right, you could write down this stuff on this slide. Not a bad idea. If it makes perfect sense, that's great. So I wouldn't bother writing anything down on this slide as much, besides the title. Okay, this slide's a good thing to write down again. And then this slide, the big thing you need on this slide is you need to know the equation for calculating Kelvin and Celsius, because this equation will only work in Kelvin. So C plus 273 equals Kelvin. Okay, so C plus 273. Okay, so 1 second. Go next slide here. Okay, so here's the math that led to those graphs there. Okay, that that Charles in this case calculated a constant. Okay, if you look here, so it was volume equals this constant times temperature, or you could write it this way. Okay, but if you do V over T here and solve for the constant, that means if you change your temperature, your volume is going to change too. So since you make it equal to the constant, okay, the original volume divided by the original temperature equals the constant. And then if it changes, let's say it gets hotter or colder, or even if the volume gets squeezed or something like that, what will happen is it actually changes the temperature too. So it works better if you don't take pressure. You have to assume pressure stays the same, and that's why if you squeeze it, you'd increase pressure. So it involves certain things. So that's why it's easiest to measure in the way of us changing the temperature, okay, and then letting the volume react to that, okay. But pressure needs to stay the same, and the number of particles, the moles of gas, needs to stay the same, okay. So it's volume divided by temperature equals this, and then so on. So here is the thing you need to actually write down here. This is actual Charles' law. Volume 1 over temperature 1 equals volume 2 over temperature 2. Okay, we're now going to go ahead and do some practice problems, and so we feel all good about that. So here we go. Number 1. Okay, let me go ahead and write. So remember, it is V1 over T1 equals V2 over T2. Okay, so read our little story here. So we have 4.0 liters of gas, and it's collected at 278 Kelvin. And then we heat it up to this new number of Kelvin, and the pressure stays constant, so that's good. Does the gas expand or shrink? What's this new volume? Okay, so you could figure this out, the first part, by asking yourself, we start at 278, and we go up to 351. Pause this and think, expand or shrink. Hopefully you said expand, because it got hotter, moving faster particles take up more space. So yeah, I hope you said expand. Okay, but we need to do the math to figure out the new volume. Okay, since it's already in Kelvin, we can use numbers as is. Okay, so in this case here, volume 1 is 4.0 over temperature 1, 278 equals, okay, and we're trying to find V2, so I'll put V2 right there, okay, but we do know T2, which is 351, okay. So we're now going to cross multiply, and that means if you cross multiply, you take the top number on one side and you multiply it times the number on the other. So in this case here, I'll go 4, enter in my calculator, 4 times 351, and I'm ending up with 1,404 equals, and then you go this times this, you cross that, so you end up with 278 V2. Okay, so you divide that 4,000, you have both sides by 278, 278, divide both sides by 278. Okay, and I'm ending up with, and you won't be able to see in the corner, but my number's just over 5. Now, I'm looking at sig figs here. So it looks like 2 sig figs because of 4.0. So now my number is 5.05. So I'm going to round it to 5.1, and it will be liters. Okay, so 5.1 liters is actually my answer will be. Cool. I'm going to go back. I'm going to go ahead and wipe that clean. We'll go ahead and do another. We're going to do a total of 3 practice problems. Okay, so here comes number 2. Okay, 1 second. Here we go. A sample of gas is gathered at 55 degrees Celsius. Okay, again, it says 1 atmosphere. Okay, the volume is measured at 9.5 liters. We put the gas in the freezer and it cools to -10 degrees Celsius. What's the new volume? So we need to, in this case here, we need to go ahead and convert. We need to convert these degrees Celsius into Kelvin. And remember, Celsius plus 273 equals Kelvin. Okay, so in this case here, 55, I'm going to add 273 plus 273 comes out at 328. And this negative 10 plus 273 comes out at 263 Kelvin. That's a 6. Okay, so we got our numbers now. Okay, and remember we're doing again V1 over T1 equals V, that's not one. Oh, equals V2 over T2. Okay, so original volume is 9.5, 9.5. Okay, and it goes over our original temperature, which is 328. Okay. And that is going to equal, okay, that is going to equal, in this case here, we don't know V2 still, so we'll solve for that. And then it's 263 on the bottom. Okay, so what's the new volume? So again, I'm going to cross multiply 9.5 times 263. 9.5 times 263, and I'm ending up with 249.8.5, big number, equals 328 V2. Okay, so I'm going to divide both sides by 328. That'll get rid of the 328. Bye-bye. Okay, and so the 2000 number, 2498.5 divided by 328, and I'm getting 7.617. That's a lot of numbers there. Let's see how many sig figs. Looks like 2 sig figs here. So it'd be 7.6. And it's a volume, and we started with liters. So it'd be 7.6 liters would be our answer. If you pause and think about it, that would make sense. You got cooler, 328 to 263. So you should get smaller, 9.5 going to 7.6. So hopefully this is making sense so far. So let's do one more. Okay, final one. A balloon has a temperature of 40 degrees Celsius and a volume of 2.1. A student puts it in a freezer and later measures the volume at this. Okay, what is the temperature of the balloon when measured the second time? Okay, so we need to convert this. Remember, 273 plus C equals Kelvin. So we need to add 40 degrees plus 273, and that gives me 313. Okay, so, and we're doing the equation V1 over T1 equals V2 over T2. Okay, so it looks like, hey, I'm recording a video right here, so it's fine. I'll come find you a little bit. So, so it looks like we start with 2.1 over 313, and that's going to equal 1.5 over what we're solving for, which is the second temperature, T2. Okay, and we just start by cross multiplying 313 times 1.5. So 313 times 1.5, and I'm getting 469.5. Okay, and then you would, that's going to be equal to 2.1 times T2. So then you divide both sides by 2.1. Okay. And it ends up being 200, and let's see how many sig figs are, well, this only has 2 sig figs. I'm getting 223.5. I should round it 2 sig figs, so like 220 would be 2 sig figs. And it is in Kelvin, 220 Kelvin. So does that make sense? Yes, so the balloon got smaller in the freezer. So that means it got colder in the freezer, and 220 is definitely colder than 313. So that does make logical sense. So hopefully this all is starting to click for you a little bit. Today will be more practice. You can see the assignment right there, and you can kind of see it in the video too, or on the Canvas page too. Use the links. Good luck, and let me know if you have any questions or need any help. Thanks.